Section 7.3, Trigonometric Substitution. In this section, we want to tackle integrals involving the square root of a squared minus x squared, the square root of x squared plus a squared, or the square root of x squared minus a squared. We will accomplish this by using an appropriate trigonometric substitution and associated trig identities to compute the integral. Let's look at an example. Consider the integral of the square root of 1 minus x squared dx. Notice that a regular u substitution won't work here. The key here is that when we see a square root of an a squared minus x squared, we need to use the substitution x equals a sine theta, where theta is between minus pi over 2 and pi over 2, so that the sine of theta is greater than or equal to 0. Notice this isn't a regular u substitution because we're not using u here. Rather, we're replacing x in the integral with a sine theta. Here our a is 1, so x equals 1 sine theta. Then dx is cosine theta d theta, highlighted here in green. Then our given integral, once we replace the x with sine theta and the dx with cosine theta d theta, becomes this new and perhaps more complicated looking integral. But we'll see with a little trigonometry that things will simplify very nicely. Here we have the square root of a 1 minus sine squared theta. We'll just use our standard trig identity to rewrite that as cosine squared theta. The square root of cosine squared theta times cosine theta d theta. Now the square root of cosine squared theta is the absolute value of cosine theta. Remember that in general, the square root of u squared is the absolute value of u, not u. But if we know that our variable is greater than or equal to 0, then the absolute value of u is the same as u, and we've made sure that that happens by this restriction on our theta. So returning to the integral, we get the integral of the cosine of theta times the cosine of theta d theta, which is the integral of cosine squared theta d theta, and we've solved this integral by a variety of methods in section 7.2, so we won't redo that work here, but instead you can compute that and see that we get 1/2 theta plus 1/2 sine theta cosine theta plus an arbitrary constant. Notice here our answer is in terms of theta, even though the original problem was in terms of x, so we need to convert back to x. To convert back to x, we just use a little geometry that's based on the form of our substitution. Remember, we use the substitution x equals sine theta, which I'll rewrite here. If x is equal to sine theta, that says sine theta is x over 1. That means if we were to draw this right triangle with reference angle theta, then sine of theta is x over 1, so that means the opposite side across from theta is x, and the hypotenuse in this triangle is 1. Knowing these two sides in this right triangle, we can solve for the third side using the Pythagorean theorem. Once we have the triangle filled out, we can then deduce the values of the parts that are resulting in this integral. So we need to know what theta is. Well, if x is sine theta, then theta is the sine inverse of x. We have that here. Sine of theta, we just read off the triangle as the opposite over the hypotenuse, so that's just x. The cosine of theta is the adjacent over the hypotenuse, so that's the square root of 1 minus x squared over 1, or just the square root of 1 minus x squared plus our constant. Notice that the idea here was when we were confronted by this integrand that is of the form the square root of a squared minus x squared, we used the substitution x equals a sine theta, and then we just patiently chipped away at this integral using a combination of algebra and trigonometry until we eventually got a doable integral in theta. Once we did the integral in theta, we have to remember to convert back to an antiderivative in x using a little geometry. Okay, let's look at another example. Consider the integral of 1 over the square root of x squared plus 9 dx, which we can rewrite as the integral of 1 over the square root of x squared plus 3 squared dx. The key here is our integrand involves a term that looks like the square root of x squared plus a squared. When we see this, we want to use a substitution. Remember, it's not a regular u substitution, but rather the trigonometric substitution, x equals a tangent theta. Here our theta is between minus pi over 2 and pi over 2, so that we're guaranteed that our tangent of theta is greater than or equal to 0. Here our a is 3, that's why I rewrote the 9 as a 3 squared. So we let x be 3 tan theta. Then dx is 3 secant squared theta d theta. We know looking at this integrand, we need to replace the x squared plus 9, not just x squared, but x squared plus 9. So we can either compute it later or we can compute it now. I like to compute it right now, but I am peeking ahead at this. If our x is 3 tangent theta, then x squared plus 9 would be 3 squared times the tangent of theta, quantity squared, which is 9 tan squared theta plus 9. If we factor out our 9, we get 9 tan squared theta plus 1. By our basic trig identity, the tan squared of theta plus 1 is known as secant squared theta. Now we'll take this, replace in our integrand what we had here with 9 secant squared theta, and then our dx is 3 secant squared theta d theta. We'll simplify this. Notice this is the square root of 9 secant squared theta, so that's 3 absolute value of secant theta. The 3's here cancel. Since by the range that we had on our trig substitution, the secant of theta is greater than or equal to 0, so the absolute value of secant theta here is the same as secant theta, and then we can cancel one of these factors of secant theta. We end up with an integral in theta that's the integral of secant theta d theta. This is a tricky integral, but remember we did this at the very end of section 7.2. It's in our repertoire. This is the natural log of the absolute value of secant theta plus tan theta plus an arbitrary constant c. Since we started in the x variable, we need to make sure we finish in the x variable, and finishing the conversion from theta to x is always by drawing one of these triangles, using our substitution, filling out the rest of the parts of the triangle, and reading off the values that we need in our theta antiderivative. So here we know that x is equal to 3 tan theta. That says tan theta is x over 3. So when we draw this right triangle with reference angle theta, we know the opposite side is x, the adjacent side is 3. By the Pythagorean theorem, we can solve for the hypotenuse. Once the triangle is filled out, then we just look and we say, we need to know the tangent of theta, which we already know, and we need to know the secant of theta. The tangent of theta is x over 3, so we put that here. The secant of theta then would be the ratio of the hypotenuse of this triangle to the adjacent side of theta. So that would be the square root of x squared plus 9 over 3. Once we substitute those in, we have the antiderivative of the original integral that we seek. Let's look at another example. If we had the integral of 1 over x squared times the square root of x squared minus 16 dx, again, we're looking for a particular form. When we have the square root of an x squared minus an a squared, we want to use the substitution x equals a secant theta. And that's going to be true even if we have some other items in our integral. This is the part of the integral that we want to key on. So when we see a square root of an x squared minus an a squared, we want to use x equals a secant theta. Again, we're choosing a range on theta to guarantee that certain trig functions have certain signatures. Okay, so we want to use here, if we rewrite the 16 as a 4 squared, we want to use x equals 4 secant theta. Then our dx is 4 secant theta tan theta d theta. Peeking ahead at this integral, I see that we're going to need to replace, we need to calculate x squared because we need to replace it, and we need to calculate x squared minus 16 so that we can put it inside the square root. So straight away, x squared is 16 secant squared theta. I'll go ahead and calculate x squared minus 16 over here. We said that x squared was 16 secant squared theta minus 16. We'll factor out the 16, use our standard trig identity, and rewrite this as 16 tan squared theta. When we replace this, highlighted in yellow, we get this. Don't forget about your differential. dx is 4 secant theta tan theta d theta, and now we've done a wholesale conversion from an integral in x to an integral in theta. And it looks more complicated, but when these integrals have the forms that we're talking about, the trigonometry and the algebra are going to work together to simplify this into a doable integral. We just have to be patient. So here we'll simplify this. We'll write the square root of 16 as 4. The square root of tan squared theta we will write as the absolute value of the tangent of theta. This just is what it is. Since we made sure we chose a range that made our tangent greater than or equal to 0, we know the absolute value of the tangent of theta is the same as the tangent of theta. We can then cancel this tangent of theta with this tangent of theta, cancel one of these factors of secant, cancel the 4's, and when all of the algebra dust settles, we have a 1 over 16, we have a 1 over a secant theta d theta. That's the reciprocal of secant theta, which is also known as cosine theta. That's a very straightforward integral. We get 1/16 sine theta plus c. It's very tempting to stop here, but you just need to peek up here. If we started in the x variable, we should finish in the x variable. So now we need to draw our triangle, use our substitution, fill out the parts of our triangle. We knew that x was 4 secant theta, so secant theta is x over 4. That means the hypotenuse in the triangle is x. The adjacent side must be 4. Using the Pythagorean theorem, we can find the other side. And now when we have all the sides, we can find whatever trig functions we need. In this case, we need to find the sine of theta. So the sine of theta is just the opposite over the hypotenuse. So we get the square root of x squared minus 16 over x. We replace sine theta with that, and we have the antiderivative that we seek. Let's look at one more example on how to handle a situation when the given integral doesn't exactly match one of the three forms that we had before. Sometimes you have to do a little algebra in order to manipulate the given integrand into a form where you can execute one of the substitutions that we talked about earlier. So take a look at this one where we have the integral of dx over x squared plus 2x plus 3 all raised to the 3/2 power. If you look at this, it does not exactly match one of the forms that we had, but if you take the x squared plus 2x plus 3 and you were to complete the square, so here you write this as x squared plus 2x plus the number that's going to complete the square, plus 3, and then we'll subtract off the number that's going to complete the square to maintain equality. If you remember from algebra, when you have a leading coefficient of 1, the way you compute the number that completes the square is you take the coefficient of the x term, you half that number, and then you square the result. The resulting number is the number that completes the square, so I'm going to write it here. I'll turn around and subtract it right back off in order to maintain equality. And now this is a perfect square trinomial, so this will always factor into x, this sign, and the square root of this number, quantity squared, and then this part just is what it is. In this case, it's a 2. I'll rewrite that as the square root of 2 squared because I want to keep in mind with the theme that I want things to look like a sum of squares in order to match one of the substitutions that we used earlier. Notice it doesn't quite match one of the substitutions because of this shift, and we'll show you how to handle that in just a second. So our original integral was this. We rewrote this part of the integrand as this. This is starting to look like a sum of squares, but it has this shift in it. So why don't we do a regular u substitution, let u be x plus 1, then du is dx, and now this shift here, highlighted in yellow, is a shift no more, and this integral now becomes this. This really is of the form of the types of integrals we've been looking at. It has a u squared plus a squared, where our a is the square root of 2. And so now we'll let u be a tan theta. In this case, u is the square root of 2 tan theta. Calculating our du, we get square root of 2 secant squared theta d theta. And now we'll just substitute. Our du is highlighted in green. Our u here, you can do this now or you can do it later. Our u is the square root of 2 times the tangent of theta. I know that I need to compute all of this part here that's underlined in orange. I'll go ahead and do that now. This is the square root of, this is u squared plus 2. So u squared is just 2 times tan squared theta. Add 2, factor out the 2, rewrite this as secant squared theta using our standard trig identity. And now all of this in the brackets becomes a 2 secant squared theta. It's still raised to the 3/2 power. We'll handle that in a second. How about we distribute this 3/2 power and write this as a 2 to the 3/2? We'll write this as a secant squared to the 3/2. There's a variety of ways that you could handle this algebraically. This is just one of them. And now I could simplify this as a 2 to the 1/2 power, a 2 to the 3/2 power. So I should end up with 1 power of 2 in the denominator. I can think of the secant squared theta to the 3/2 as the secant squared of theta to the 1/2, all raised to the 3rd power. And when you compute that, you get the absolute value of secant theta quantity cubed. But by how we had set up our substitution, secant of theta here is greater than or equal to 0. So secant, the absolute value of secant theta is just secant theta, and it's still cubed. Here we have 2 powers of secant. Here we have 3 powers of secant. We'll cancel 2 of those powers. That will leave us with a 1/2 that we'll pull out of the integral. We'll have a secant in the denominator, which when we reciprocate that becomes a cosine theta in the numerator. And we end up with a very doable integral in theta that's 1/2 the integral of cosine theta d theta. Straight away, that's 1/2 sine theta plus c. Now this is an integral in theta. We need to convert back from theta, and if you remember our substitution related u and theta. So if we're going to convert back from theta, we first have to convert back to u. And so we'll draw our triangle. Our substitution was u equals the square root of 2 tan theta. We'll draw our triangle like we always have with reference angle theta. Then tan theta is u over the square root of 2. So the opposite side in this picture is u. The adjacent side is the square root of 2. Using the Pythagorean theorem, we'll compute the hypotenuse. And now we have our triangle fully filled out, and we can answer whatever questions are needed of us. Here we need to know the sine of theta. The sine of theta is just the opposite over the hypotenuse. We'll replace that here, and now we're back to an antiderivative in u. We're still not done because we have to finish with an antiderivative in x, but we went from theta back to u, and now we'll go and use our regular u substitution to convert back from u's to x's. So if we convert back from u's to x's, then we get our u was x plus 1, our u was x plus 1, and you could write this like this. This is totally fine, or you could expand this out, and this is what was contained in the original integral. Okay? So to summarize, a nice summary strategy of how to attack these problems, because you don't want to be just mechanically going through the motions. You want to be able to think through what are the relevant pieces in each one of the problems that you face. Really, there's 3 major patterns or templates that you're looking for. When you see the square root of an a squared minus an x squared, you always want to use the substitution, x equals a sine theta. Along the way, you're going to need to compute this quantity. And the way you could either do it for each individual example, but you'll see that over and over, every time when you have the square root of a squared minus x squared, when you make this substitution, after you apply the trig identities, this is going to be an a cosine theta. So that's sometimes handy. I don't know that you should necessarily memorize it, but you can check your work against it. And your triangle is always going to look like, well, if x is a sine theta, then sine theta is x over a. So the opposite side is x, the hypotenuse is a, and you can use the Pythagorean theorem to find the other side. You normally will have to use this triangle to fill out whatever the other parts are in your theta antiderivative. On the other hand, if you have an integral that involves a square root of x squared plus a squared, when you see that template or that pattern, you want to use x equals a tan theta. Along the way, you're going to need to compute this quantity, and when you have this x, this quantity always comes out to be a secant theta. And then you're going to need to fill out your triangle. Since x is equal to a tan theta is a over x, so your opposite side is x, your adjacent side is a, and using the Pythagorean theorem, you can fill out the third side, and now you can answer whatever questions you need to convert your theta antiderivative back to x. Last but not least, if you are confronted with a square root of x squared minus a squared, you need to use x equals a secant theta, and then when you compute this, after you apply the trig in the algebra, this will be a tan theta. Again, your secant theta is x over a, so when you draw your triangle out, you're going to get a hypotenuse that is x, an adjacent side that is a, and then you can use the Pythagorean theorem to find the third side. I really want to stress that you shouldn't necessarily be memorizing this, just robotically memorizing this, but you do need to pattern match. When you see this, you have to know what substitution to use, and then you have to be able to flesh out your triangle using your standard trigonometry.